Chapter 6. Clocks. We pop A6 and we append C6. The new constraint: in real distributed systems, there is no universal notion of time. Each machine maintains its own local clock, typically driven by an inexpensive quartz oscillator. Because distinct oscillators drift at different rates, clock skew inevitably develops between machines over time. Time in a distributed system is therefore relative, not absolute. Watch the three oscillators on the diagram diverge from true time as the seconds elapse. None of them is broken. They're simply independent physical devices, and independent physical devices do not stay in step. The immediate consequence is that the precise global order of events can no longer be determined from timestamps alone. And that undermines, in particular, the last right wins conflict resolution strategy we relied upon in chapters 4 and 5, because those results depended on timestamps faithfully reflecting true chronological and therefore causal order. I want to be very concrete about how bad this is, because it's easy to mistake it for a mere ordering nuisance. Consider two writes. The first happens on a node whose clock runs fast, and it's stamped with a relatively large value. The second write happens genuinely afterwards. It was caused by the first, but it happens on a node whose clock runs slow, so it carries a smaller timestamp. Now apply last write wins. The system compares the two numbers and keeps the one with the larger timestamp, which is the causally earlier write. The causally later write is silently discarded. That is not an ordering anomaly. That is data loss. The content of the later write no longer exists anywhere in the system. A timestamp was evidence. Under C6, it is merely a number that a machine wrote down. This chapter's job, then, is to recover ordering guarantees without a trustworthy global clock. And note that A7 still holds throughout. No node has yet crashed. Let's begin with the approaches that try to salvage physical time before we abandon it. Even without a perfect global clock, several mechanisms narrow the practical impact of clock skew. And two. First, monotonically increasing transaction identifiers can be used for sequence ordering within a single leader replication scheme, sidestepping any need for wall clock time at all. If one node is already the sole sequencer of writes, it can simply count. The limitation is equally clear. This only works for designs that have a single sequencer. It's useless for multi-leader or leaderless architectures. Second, and more sophisticated, clocks can be modeled as reporting a confidence interval, a bounded range guaranteed to contain the true time. A process can then wait out the width of this interval before committing a transaction, ensuring that the intervals for causally ordered transactions do not overlap, and thereby preserving a consistent, externally observable order. Look carefully at what that mechanism costs, because it's unusually honest. To know that your ordering is externally correct, you must deliberately do nothing for the width of your own uncertainty. The weighting is the mechanism. Bounded uncertainty schemes of this kind, combining GPS and atomic clock references, are used in some globally distributed database systems to bound clock uncertainty to a few milliseconds. Third, atomic clock-based synchronization more generally is used to keep clock skew within acceptable bounds across a fleet of machines, improving the reliability of any mechanism that depends on a proximate wall clock agreement. And a classic implementation for keeping physical clocks in approximate agreement is the Network Time Protocol, or NTP, a hierarchical synchronization scheme in which atomic and GPS reference clocks occupy the top stratum, and each successive stratum synchronizes from the one above it over an IP network, with synchronization accuracy degrading at each progressively lower level from the global reference. All three of these approaches narrow the problem. None of them removes it. So the rest of the chapter abandons physical time and orders events logically instead. To do that, we first need to be precise about what kinds of order there are. Event ordering in a distributed system can be either a total order or a partial order. A total order places every pair of events in a definite sequence, regardless of whether the events are causally related, yielding a single comprehensive timeline of all system activity. A causal or partial order, by contrast, orders only those pairs of events that are causally linked NUID, leaving causally unrelated events unordered with respect to one another. Now, a related practical matter, since total order comes up constantly in system design, unique identifiers are frequently used to impose a total order without coordination between nodes. Randomly generated schemes, UUID version 4, are unique but carry no ordering information at all. Time-ordered schemes, UUID version 7, Place a timestamp in the high order bits so that identifiers sort in approximately the order they were generated. But be careful with that word approximately. The order a time-ordered identifier induces is only as trustworthy as the clock that produced it, so it approximates causal order rather than tracking it. Which raises the question, what does it mean precisely for one event to cause another? The happen before relation, written with an arrow, defines a strict partial order over events, capturing causal dependency. If event E1 happened before E2, then E1 may have causally influenced E2. This relation is transitive. If E1 happened before E2 and E2 happened before E3, then E1 happened before E3. And two events for which neither direction holds, neither E1 for E2 nor E2 before E1, are said to be concurrent, written with the parallel bars. They are causally independent and may be observed in either order or simultaneously, without violating causal consistency. I want to stress the meaning of concurrent here, because the everyday meaning of the word actively misleads. Concurrent does not mean at the same time. It means there is no path of influence in either direction. On the space-time diagram, a causal edge exists only along a process's own line or along a message. Nothing else creates one. Two events can be separated by hours and still be concurrent, if no message ever connected them. And that is exactly what remains knowable once clocks are untrustworthy. Not when things happened, only which events could have influenced which. So how do we track that relation mechanically? Logical clocks are integer counters, initialized to 0 at each node, that serve as a proxy for local and global logical time. Each node increments its counter by 1 whenever a local event, a message send, or a message receive occurs. That simple mechanism is the basis for the two schemes that follow. A Lamport clock is a per-node logical clock that is incremented by 1 immediately before each local event. Outgoing messages carry the sender's current clock value. On receiving a message, a node sets its own clock to the maximum of its current value and the received value, then increments by 1 before processing the message. Trace that rule on the worked example, and you'll see the guarantee it produces, an ordering of events that is consistent with causality. If E1 happened before E2, then the Lamport timestamp of E1 is less than that of E2. Two limitations follow, and they matter. First, because two events on different nodes can carry equal timestamps, obtaining a genuine total order requires an additional deterministic tie-break conventionally on node identifier. Second, and much more importantly, the converse of the causal property does not hold. A smaller Lamport timestamp does not imply a causal relationship. On the trace, you can find an event with timestamp 1 on a third process that is concurrent with an event carrying timestamp 3. The numbers suggest an ordering that causality does not support. So the Lamport condition is necessary, but not sufficient, for causal precedence. Lamport clocks are therefore suitable for establishing a total order, but insufficient, on their own, to recover causal relationships between arbitrary event pairs. Their cost profile is 1 integer per node, nearly free. And that's exactly what they buy and exactly what they cannot. Vector clocks make that condition both necessary and sufficient. A vector clock generalizes the logical clock into a vector of length n, with one entry per node in an n-node system. Each node increments only its own entry when it performs an event, including message sends and receives, and attaches its current vector to every outgoing message. On receiving a message, a node updates each entry of its own vector to the maximum of its current value and the corresponding entry in the received vector. Vector clocks satisfy what's called the strong clock condition. Event E1 with vector clock V1 happened before event E2 with vector clock V2 if and only if every entry of V1 is less than or equal to the corresponding entry of V2 and at least one entry is strictly smaller. That if and only if is the entire point. Because the condition is both necessary and sufficient for causal precedence, unlike the Lamport clocks condition, which is only necessary if vector clocks allow the causal partial order between any two events to be recovered exactly from their timestamps alone. Which means comparing two vectors yields three possible verdicts, not two. Either the first is dominated by the second, so E1 happened before E2, or the second is dominated by the first, so E2 happened before E1. Or neither dominates, in which case the two events are genuinely concurrent, and we know it definitively. That third verdict is the thing a scalar clock could never give you. And the cost of having it is storage and comparison overhead linear in the number of nodes. Expressiveness versus overhead in one line. Now let's take that same idea and point it at a different object. Version vectors apply the same underlying mechanism as vector clocks, but to the partial ordering of operations on individual data items MTT, writes, updates, deletions, rather than to events in general. They function as a per-item version control mechanism in the presence of clock skew. The mechanics are familiar. Each version vector begins with every entry set to 0. A local update increments the entry corresponding to the writing node. During synchronization, two replicas vectors are merged element-wise by taking the maximum of each entry, exactly as with vector clocks. Every write is stored together with three things: its version vector, the identifier of the client or node that issued it, and the resulting data value. And here's the payoff, which directly repairs the data loss scenario we opened this chapter with. Entries can be safely overwritten when one is causally after the other. The dominance test tells you so with certainty. And concurrent, causally unrelated writes are flagged for explicit conflict resolution rather than being silently discarded. Read that difference carefully. The point of a version vector is not to resolve conflicts automatically. The point is to know for certain that you have one, so that the choice about what to do is made deliberately rather than by accident of clock drift. There is a cost, and it grows in an awkward direction, because a version vector must be tracked per data item and must have one entry per client or server that might write that item. This approach can incur significant storage overhead in systems with many writers. Dotted version vectors are an optimization that reduces this overhead while preserving the same causal tracking guarantees. We now have what we need to revisit the consistency analysis of chapters 4 and 5 in light of clock skew. And I'd encourage you to compare this table directly against the one from chapter 4, row by row. For synchronous single leader replication, the earlier results are unaffected. The leader still sequences every write itself, and every follower applies updates in that same leader determined order, independent of wall clock time. And the asynchronous single leader case is likewise unaffected. Its ordering never depended on timestamps either, since monotonic transaction identifiers suffice. Note why those rows survived, because it's the general lesson hiding in the table. The leader never needed a clock. Centralized ordering is robust to clock skew by construction. For multi-leader and leaderless replication, however, the earlier reliance on last write wins conflict resolution no longer holds up, because C6 means timestamps across nodes can no longer be trusted to reflect true chronological and therefore causal order. Last write wins can now violate causal consistency outright. And in the worst case, it can silently discard a causally later write in favor of an earlier one that merely carries a larger skewed timestamp, resulting in genuine data loss rather than a mere ordering anomaly. Shostan. Both of those rows are therefore downgraded from causal consistency to eventual consistency only. Achieving causal consistency under multi-leader or leaderless replication now requires version vectors or an equivalent causality tracking technique. In case of naive timestamp comparison, absent such a mechanism, only eventual consistency can still be guaranteed. I want to draw attention to what just happened because it is the clearest demonstration of why this course is ordered the way it is. A mechanism that was perfectly correct for 2 chapters became unsafe, not because we discovered bug in it, but because we removed an assumption it was quietly resting on. Let me summarize chapter 6. As long as A6 held, every mechanism in the preceding chapters could treat a timestamp as ground truth. Last write wins conflict resolution in multi-leader and leaderless replication correctly reflected true causal order, simply because all clocks agreed. Constraint C6 withdraws that guarantee, since clock skew means physical timestamps across nodes can no longer be trusted to reflect true chronological and therefore causal order. And the chapter's central problem is consequently not merely academic. It exposes that the earlier reliance on last write wins can now silently discard a causally later write in favor of an earlier one that merely carries a larger, skewed timestamp, turning an ordering anomaly into genuine data loss. The chapter's mechanisms restore ordering guarantees without relying on a trustworthy global clock at increasing levels of cost and precision. Monotonic transaction identifiers and bounded uncertainty clock schemes sidestep the problem entirely for specific architectures at the cost of either being restricted to single leader designs or requiring specialized tightly synchronized clock infrastructure. Lamport clocks provide a cheap, scalar order consistent with causality, but cannot by themselves distinguish a causal relationship from a coincidental one. Vector clocks, together with their per data item specialization as version vectors, satisfy the strong clock condition and therefore recover the true causal partial order exactly, at the cost of storage and comparison overhead that grows with the number of nodes or writers, and overhead that the dotted version vector optimization partially reclaims. The trade-off throughout is expressiveness versus overhead. Since a scalar Lamport clock is nearly free but cannot detect concurrency, while a full vector or version vector detects concurrency exactly but costs space linear in the number of writers. And that trade-off is compounded by a second one, between logical mechanisms, which need no special infrastructure but carry no wall clock meaning, and physical bounded clock mechanisms, which are directly usable for external consistency but require investment in specialized hardware. One clarification worth holding on to, since the two are easy to conflate. Vector clocks and version vectors share a heuristic, one counter per node, element-wise maximum on merge, a dominance test for after. But they answer different questions about different objects. A vector clock orders events in an execution, asking whether E1 could have influenced E2. A version vector tracks writes to one data item, asking whether this copy may override that one, or whether both must survive. Same machinery, different purpose. In practice, systems that only need a consistent total order, such as event logging or single leader sequencing, can rely on Lamport clocks or transaction identifiers. Systems running multi-leader or leaderless replication that must detect genuine write conflicts rather than silently resolve them by unreliable timestamp should adopt version vectors regardless of the added bookkeeping. And globally distributed systems that require strong, externally consistent guarantees across regions should consider bounded uncertainty clock infrastructure only when the cost of atomic clock synchronization and commit weight latency is justified by the application's consistency requirements. There's no causality tracking mechanism that is simultaneously free, precise, and infrastructure independent. One assumption remains on the stack, and it's the one we've been deferring to since the very first chapter. First chapter. Nothing ever fails. The next pop is the last one, and it forces a re-examination of every mechanism in the previous 6 chapters.